Okay, we're looking at parametric equations today. So far, when you guys look at equations, you look at X and Y, right? You have X, you have Y, and you work it out. But a lot of things that we deal with happen in time. Like if you were to hit a golf ball, it'll have an X distance, right? It leaves and it goes far away. It will also have a Y distance because it's going to go up in the air. And both X and Y happen together with time, right? It takes a few seconds for your ball to hit the ground. So we've got X, we've got Y, and we've got time. So that's what parametric equations are. You'll use your calculator. Now, I'm going to teach you today how to do it just using what you've always used. You're going to use the Y. We can make it work with both. Next block, I'm going to at least demonstrate for you a problem where I just have to show you how the parametric. So if you go into mode, don't do this with your calculator now. I'm going to teach you how to do it so you can just use function mode, which is the natural habitat of your calculator. We're going to learn what's going on, and I'm going to demonstrate what it looks like in parametric equations for you next time. So if I were to go into parametric and I go to Y equal, you notice I have X and Y. It puts time in there. We can also put time in using function if we play with it a little bit. So to introduce it, I'm going to leave my calculator in function mode, show you how to do that so it's not two different things. Then next time, once you're used to what the idea of parametric is, I'll demonstrate really quick for you what it looks like if we use the parametric mode, okay? So you definitely need a calculator. So let's look at this. What is a parametric equation and why do we need them? Let me throw my pen on the floor. Parametric equations are equations that express two different variables in terms of a third variable called a parameter. So for us, most of the time, our parameter is time, right? Everything we do, we measure with time. I hit the ball. How long did it take it to get to the ground? I threw a baseball. If I throw a baseball, it goes X direction to someone, but it goes up in the air. Eventually it falls in their glove. Time goes by. We measure everything in time, right? How long is this class? How long is lunch? How long to get to Dunkin' Donuts and back? Everything's time. So parametric equations come in pairs. The following set of parametric equations describe X the distance and Y the height as a function of time. In this example, the parameter is time. And for most of the things we do, the parameter is time, okay? Make a chart of values, then graph the relation X, Y, and indicate the direction of movement. Okay, so right here, and I don't like this problem because it says -2t to 3. What's wrong with that? Are you ever going to get this problem? What's wrong with this problem? Time is negative. Time is never negative. Should we change that? Well, we can't change it. Yeah, we could. I'm going to leave it, but let's, in practice, time is never negative, right? We're just doing a problem on paper just to show you how to graph these. So here's how this would work. If I'm going to put in time, I'm going to use what they gave me. Actually, you know what? I'm not going to do those two. I can't bring myself to put in a negative time. I just can't do it. So we'll start with 0. So notice here we have X and we have Y. So we're just going to plug it in, take 0 and plug it in. If you plug 0 in for X, what do you get? For T right there for the X equation. -3. If you plug 1 in, what do you get? If you plug 2 in, and if you plug 3 in, 0. Now we're going to take 0 and plug it into the Y part. If you put 0 into Y, what do you get? Plug 1 in, plug 2 in, Plug 3 in, 9. So now we have the points that you're used to graphing. Can you now graph those? Yes, you can. Negative 3, 0. Negative 2, 1. Negative 1, 1, 2, 3, 4. 0, 9. Well, it goes up here, right? If I were to plug a negative 1 in, right? If I were to plug a negative 1 in, I would get negative 4 and I would get 1. So negative 4, 1. I just want to show you that this is a curve. We know it's a curve because of t squared. The one thing you need to do is where you start and we draw arrows. You draw your graph in. Now it stops right here because we said that time only goes to 3 seconds. But when you draw one of these, you always put arrows to show which direction it's going, right? When you throw a ball, you need to know which way it's going. So see how easy that is? We had two different equations. We had an equation for x and an equation for y. We plugged time into both of them, and then we got x, y points that we're used to. And we always show direction. That's not bad, is it? That was easy, right? Okay. What about number 2? Find the rectangular equation with restrictions and graph the parametric curve using this equation. Don't forget to indicate your initial point, direction of motion, and check with the calculator. That sounded scary. What's a rectangular equation? It's x, y. It's what you're used to. Your entire life, you've done rectangular equations. That's where we're using, you know, x, y, like 3, 4. You're using what you're used to. So can we make one equation out of both of these? Yes. How are we going to do that? Kind of. Do you remember a long time ago? You don't have to write this down. If I gave you this, if I gave you those two equations and they were both y, what was true about this and this? They were equal to each other. So we need to get these equations equal to the same variable. So what variable are we going to get them equal to? T, of course. So I'm going to write this here. I'm going to write that over there. So we're going to get, oops, I was ahead of myself. So now what are we going to do? We're going to subtract, right? Square root of t equals x minus 2. And what do we do to get that t out of the square root? Yeah, we have to square both sides. So t equals x minus 2 squared. Now, I don't have to do anything with that. That's fine. And what's this one going to be? We could, or right here, we have y equals, right? Our goal is to get rid of t. Do I already have t? Can I replace this t with that? I could. I can shorten my time up. I could set them equal and then I'd have to get y by itself anyway. So I could just say 6 minus t. Now you probably don't like how that's written. What is this creature? You've graphed him before. What is he? Quadratic. It's a quadratic. Now you usually like it written like this. That's your preferred method of writing it, right? I didn't change anything. This is still negative. This still goes here. So what's the vertex of this guy? 2, 6, right? 2, 6 is the vertex. Okay, let's graph that. 1, 2, 1, 2, 3, 4, 5, 6. All right. Now, do I have to make a chart or can I graph a parabola? Do you already know how to graph that? I'm going to make a table so that your brain will see how these go together. We need t, x, and y. So where does t is greater than or equal to 0? So if you plug a 0 in for t, right? If you plug a 0 in for t, what is x? Go back to your equations. If you plug 0 in for t, what is x? Right here, y'all. If you put 0 in for t, what's x? 2. If you put a 1 in for t, what is x? Now, I don't want to put a 2 in for t, do I? What's the next number I want to put in for t? 4, because 4 is a perfect square. And what's the square root of 4? 2, and what's 2 plus 2? Okay, now let's take these same t's and plug them into y and see what we get. What is 6 minus 0? What is 6 minus 1? 6 minus 4. Now do I have x, y points that I can graph? And what do you notice about what you told me from prior knowledge? You already knew one of the points, and that point showed up, didn't it? Right? Okay, so 1, right? 3, 5, 1, 2, 3, 1, 2, 3, 4, 5, 4, 2. 1, 2, 3, 1, 2. Right? Right? So I got this curve. Now, did you need this table to graph a parabola? No, because you know a parabola is a squaring function. So if you shift over 1, 1 squared is 1. If you shift over 2, 2 squared is 4. So if you shift over 3, 1, 2, 3, how far down are you going to go? What's 3 squared? So I know my next point would be there, right? Can I graph it using the table? Yes. What happens if you put 9 in for time? What's the square root of 9? 3 plus 2. And if you put 9 in here, 6 minus 9. And that's where that point is, right? Does that make sense how these work together? So I want you to think about what you know. You can pick times and plug them in and make a table and get your x and your y, right? Or you can solve each equation, one of the equations for time, and then you can plug time in and you have a y equals. This is your rectangular equation. It's what you're used to. You got time out of there. Do we get the same picture with this equation that we get with this table? We do, right? They back each other up. Does that make sense what's going on? This is kind of explaining to you what's happening. It's not going to look anything like the work we do. Does that give you a picture of how time can be in both of those equations? Does that make sense? Sort of? Okay. We're going to look at real problems then. Oh, good stuff. So let's put what we learned about vectors and what we know about parametrics together to simulate the motion of an object. Okay, so instead of just having x and y, when we toss a ball, bat a ball, hit a ball with a golf club, we're now going to have x, y, and time. Okay, now I want you to think about vectors or trigonometry. I'm going to say trig. What was the x value in trigonometry? Who's X in trig? Sine or cosine? Cosine. When we first started trig, we had cosine and sine. Well, let's do rectangular. That's XY, right? Rectangular is XY. Trigonometry was cosine and sine. Then last block, we introduced vectors. What did it look like for a vector? What was the X value for your vector? It was cosine, but what did it have with it? Magnitude, right? So you've been doing a lot with points in your life. You graphed XY long time ago. This year we introduced you to sine and cosine, and you'd say 1/2 square root of 3 over 2, right? Or square root of 2 over 2, square root of 2 over 2. We had X and Y. Then we looked at vectors, which had magnitude cosine theta, magnitude sine theta. Now we have parametrics. I want you to see that you're doing the same thing. You're just adding a little bit to it. What did we say parametrics were? What new variable or what additional variable did we introduce to parametrics? Time. So we're going to say, we're going to have a magnitude because you hit a ball so hard, right? With a golf club or a baseball, or even with your arm, you throw it, you have to put some energy in. So we need a magnitude. Then we're going to have this guy, time. And then we're going to have cosine theta. I'm putting the T in a different color so he stands out. Do you see how this I like to go over how this works together. Do you see what we're doing? We started with points when you were a youngling, graph 5, 6. Then we did cosine of 30, sine of 30, and you graphed those on the edge of a unit circle. Then we added in a vector, you're putting some energy in, and now we're taking what we learned and we're going to add time to it. Is it still just XY? Still just XY, right? True? Okay. Let me take this one step further. I'm going to call this parametric on Earth. Now, how many of you live on planet Earth? How many of you float? We don't. We stick to the ground, right? We wish we could float. So we stay flat. Do you move back and forth? You can move from this room to another room, right? So there's nothing wrong with X on planet Earth. But you're not able to go up. Your feet stick to the ground. So what do we do about that? What makes you stick to the ground? Gravity. Gravity affects your height, so that's a Y value, right? True? So we're going to have this. How am I going to put gravity in there? Yes, but what is it? You've been in physics. That's for meters. I'm going to write it down in feet. What's the number for feet? 16. This comes from, it's a derivative. Well, it's 32 feet per second. Yeah. That's where the 16 comes from. I can't explain the calculus to you, but if you take 2 times 16, you get 32. You'll see that next year. I can't let you in on that surprise yet. but this is gravity. I kind of taught you all the notes already, but I don't like the notes separated. I like you to make the connection rectangular, trigonometry, vector, parametrics, parametrics on Earth. If you throw something, it's coming down, right? So when we toss something in the air on planet Earth, we have to subtract this off. Now I would need to change that. If I did meters, it would just be a different number. Okay, be half of 9.8, but we're gonna work in feet just to keep it consistent. And it's subtracted because it's pulling down. Does that make sense? So I kind of spoiled it and I did all the notes, but I really like you to see where the train of thought is coming from, right? Everybody okay? All right, so now we got to try a real problem. A ball is tossed up in the air at an angle of 70 degrees with the horizontal. With the horizontal, that means the ground, right? So you're throwing a ball up at 70 degrees with an initial velocity of 36. Right now, we're going to neglect air resistance and gravity. We're always going to neglect air resistance. It's small, and that gets into some really tough stuff quickly. We will put gravity in. So in this problem, what is the magnitude? When you read this word problem, what's the magnitude? 36. What is theta? 70. Now we're going to use that to write an equation. We're going to leave t in the equation, and then we can plug t in if we want, right? So this says give the velocity vector. This is the vector. We'll put the t in when we change this to parametrics. That's why I like you to see all of these things. So if you're asked a question, you know what to answer. If it says vector, that's this. If it says parametric equation, we add in the t, which we'll do in a minute. Does that make sense? So we're pulling in yesterday. The velocity vector would be what? 36 cosine 70, 36 sine 70. And can you type those into your calculator? Let's type them in. Tell me what you get. Make sure you're in what mode? Degrees. Always check that first. Where's the natural habitat of your calculator? Well, yes, but it's also radians. So anytime you clear your calculator, it's going to go back to radians. So you want to put on that degree and make sure you're there. Okay, so 36 cosine 70. All right. So type those in. I already did to save myself a little bit of time. And what does this mean? Well, if this is positive, we're going that direction, so we're going east, right? And if the y is positive, what direction am I going? North. That's how we're going to look at those with vectors, okay? And y'all are very used to this guy, right? So x is going to be east or west because that's your horizontal motion. Y is going to be north or south because that's vertical. Does that make sense? Now, as we work through these problems, do you always need to read the problem? Yes. If a ball hits the ground, is it going to keep going into the ground? Not unless you're the Hulk or Thor, right? Maybe Iron Man. They can do it. We can't. So we have to manually read problems and stop things when it would naturally stop, right? We know no matter what an equation says for time, if the ball hits the ground, it's over. We're done, right? Okay. Specify the position as a vector 1, 2.5, and 4 seconds after the ball is released. So at 1 second, this is at 1 second, right? At 2.5 seconds, what would I have to do? I have to multiply the 36 times what? 2.5. What's 36 times 2.5? 90. You know what? I don't even like this. Okay, I'm going to do it. That's why they want it. This is getting you to put the t in there, which I've already told you exists. Right? Because that is 36 times 2.5. And then here we're going to have 36 times 4, right? What is 36 times 4? 144? And I don't care if you don't punch those in, that's fine. Express the position of a ball at time t, where t is the number of seconds after the ball is released. What they're asking you to do now is write a parametric. So now they're saying write it in the parametric form. So that's going to be what? Which I kind of tied all this together for you at the very beginning. So remember, this is vector form. This is parametric form, right? We want to know the difference. You guys know that when we work in programs like Delta Math or MathLab, what they ask matters, right? You know what I mean? When you don't get what they want and you're like, and then you type it in wrong and have to start over. So we want to be very clear. The vector form isn't including the letter T. When we get to the parametric form, we have the T. Okay, so write a general vector that can be used to model motion. I already did that for you, and that was what? I'm going to use a capital T because when we use our calculators, it puts a capital T in. Okay, how does this differ? We include time. Okay, so we just took this much time to do what I showed you up here with the comparison. Is that okay? I like doing it this way better. You think? It makes more sense. Okay. Does the description of this problem situation provide a realistic model of a thrown ball? No. We need gravity. And I already told you how to put gravity in, right? So what is gravity going to be for that same problem? 36t cosine 70. 36t sine 70. And how do we add gravity? What's our gravity? And this is 4 feet. Our problems will be in feet because most of the time, like in the US, if you're watching baseball or golf or whatever, we're in yards and feet. This number would change if it were metrics. It'd be half of 9.8. Okay, so now we want to ask some real questions. How far has the ball traveled horizontally after 2 seconds? How high is the ball at that time, right? How do I do that? Well, if I want to know horizontally, which equation do I plug the 2 into? X. Let's plug it in and see. And what do you get? Since these are word problems, we want to include the unit. Now, let's do this one. How high is the ball at that time? What are we going to plug into for height? Yes. So plug 2 into y1, and that's going to give us the height. Not hard, right? It's not bad. We just have two different equations. Time is the thing. You're used to plugging x into a y equation. Now we're taking t and we're plugging it into x and we're plugging it into y to get the different things that we want. X is going to do distance away. Y is going to do height. What do you get when you plug 2 into the y equation? Wait, what? Let me plug that in. Times 2. Yeah, you have to subtract that. Okay. So that's, I'm getting 3.658. Did you get that, everyone? Okay. Does that process make sense? This is the big idea for today. Does it make sense? So let's go back and go through that. If I want to know how far away the ball is, I'm going to plug into x because that's distance away. If I want to know how high the ball is at a specific time, then I'm going to plug that into y, and that tells me how tall it is at 2 seconds, right? All right. Does that make sense? And when you think about a ball, right, it goes in that path. How long will it take for the ball to hit the ground? What does that mean? Well, let's think about something. A ball is going to hit the ground. Can distance away from me vary when a ball hits the ground? Yes, I could toss a ball to Morgan and she might miss it and it hits the ground here. Then maybe I toss a ball to Annika and it hits the ground over there. So that distance away from me is not relevant. What's relevant is my height. What's the height of the ball at 0? I'm sorry, when it hits the ground? 0. So what am I going to do? How am I going to simulate hitting the ground? What am I going to do? Well, vertical equals 0. So which one, x1 or y1, equals 0? X or y, which one is 0 when it hits the ground? Y. So I'm going to set that equal to 0. Now, can I type it into my calculator? Yes. I'm going to say 36. Now, does my calculator care if I use the letter t or x? No, my calculator doesn't know. It just knows that's a variable. Got it? So you're just going to type here. Let me. Okay, why did that get brighter when I turn the light off? That's weird. Okay, there you go. So you're just typing that equation into y equals, right? Did I type it in right? I usually have a typo here and there. And then graph it. It takes it a second to graph. Now, this 0 right here, of course, is when it was launched or thrown, right? And this right here is where it hits the ground. So what happens is our x-axis has become time, right? Our x-axis has become time. How do you find a 0? How do you find a 0 in your calculator, guys? Second, calc, which is the trace button, and you ask it for 0. Now I want to show you something really important. Do not do this. Everyone look up here. Do not arrow around. That takes forever. All you have to do, see how it says left bound right there? So this is the 0 you're interested in. So choose a number on the left side. What number is on the left side of that 0? 1. So just say 1, enter. Now it says right bound. What's a number on the right side of this? Can you see that 3 is on the right side? You could say 3, you could say 4, any number over here. I'm going to say 3. I want you to notice what that did. What that did, do you see how it put little lines up? That's because your calculator can only look at a small piece of your screen at once. If you just ask it for 0, it sees 2 and it doesn't know what you want. What you're essentially doing when you tell it where to look is you're saying, okay, right in between these numbers, find me a 0. Okay, your calculator has to be trimmed down so it's only looking here. Once it says guess, you hit the enter key again. And how long did it take it to hit the ground? 2.114 seconds. Okay, so how do we do that? Let's see. Go to write yourself some instructions. I know sometimes we don't let you have a calculator and then all of a sudden we expect you to be experts at your calculator. And then go to second, trace, or calc, whichever word you like, 0. So you got to think about that. Where is my calculator going to hit the 0? Is that okay? Everybody good with your calculator? And we'll have time to practice. All right. Find the maximum height of the ball. How are we going to find the maximum height of the ball? It's already plugged in. Is maximum height going to be y or x? Y. So you just need to make sure this is the equation that's plugged in, and we know it is because we already plugged it in, correct? So now we just need to go where? Second, trace, or calc, and we want to find maximum. So let's go to second, trace. Maximum is choice number 4. Why does that get so bright? Can you see it now? There we go. Right? Second, calc, max. Now, what's a number? Now, do y'all agree that this is a 0 and this is a 0 and the maximum has to be somewhere in between? Do you actually have to fix the calculator to see it? Or can you tell that there's a maximum between here and here? Okay, so I'm going to say left bound 0. Right bound, I'm going to say 2 is definitely on the right side of that 0, or that maximum, sorry. Then it says guess, and I'm going to hit enter. Now let's write down that point. Maximum is at 1.057, 17.8812. That's what it gave me, right? So this means in 1.057 seconds, the ball is at its maximum height of 17.8812 feet, right? Does it make sense to you what's happening in your calculator? We're using our y equation and we're turning x into time for us, okay? Not bad. If you had this written out, you'd be okay. How long does it take the ball to travel 18 feet? Okay, let's think about this question. What do I mean when how long did it take the ball to travel 18 feet? Is that X or Y? That's the X. Because it's not talking about height. So I'm going to take my X equation and what do I want X to equal? What am I solving for? Yes. How does one get a T out of there? I want to get rid of all the other stuff. How am I going to do that? Yes. Not so bad, right? So I'm going to get the T out. Now, how do you get a fraction on your calculator? If you don't wrap parentheses around this, it'll come out wrong if you don't use the fraction button. What's the fraction button? Alpha, which is the green button, alpha y equals 1. Make sure, let's put a note, fraction, alpha y equals 1. Now you just type in exactly what you see. Why does that get so? Well, it gets brighter, doesn't it? Maybe I need to be further away. That is so weird because it's very dark under here. Well, anyway, 18, arrow down, and you're going to type in 36, cosine 70, close your parentheses. So how long is it going to take it to go 18 feet? 1.462 seconds. Everybody okay with that? And then our question is, how high is the ball at this time? So what are we going to do if I want height? Use Y. So now plug for 1.462 into the Y equation. Now, do you already have the Y equation in your thing? Is it easy to plug into that? You could just go to second window and tell it what you want. What do we want? 1.462, right? Because the equation's in Y equals. So I could, that's second window, type in the number you want and then go second table. And it's already there for you. You do not have to work. Can you just go type that into the equation? Sure. I think this is faster, right? So it will be 15.259 feet high. Is that okay? How do you feel about this? Is this okay? Yay, nay, send me home now, or I'm ready for more? It's not bad, right? What do you have to keep in mind? That when you're looking at the equations, instead of having one equation that you plug numbers into, you're plugging time in. So you have to decide, am I talking horizontal or vertical, and choose the appropriate equation, right? Not bad. And you have to remember to put gravity in there. All right, here's your test. Remember, we're working a little while today, but we don't have homework because what does this say? Class Kick Unit 6, Day 3. We will have a work day next class. So it's not homework. So let's look at this one. A baseball player hits a baseball with an initial velocity of 103 feet per second and an angle of 41 degrees. A fence is 10 feet tall and 300 feet away from home plate. Okay, so we got this baseball thing, a live problem going on. Find the parametric equations that simulate the path of the ball. What is the x equation going to be? What's our magnitude? 103, right? What's our theta? Right? Not hard. What is y? It's the same exact thing, only we have sine because sine is y. And what do we have to do so the ball doesn't continue to go up till it hits the moon? How do we put gravity in there? And sometimes you'll see people write negative 16t squared at the beginning plus this. Does it matter? I like it here because I feel like there I'm going up. Now I got to pull it down. Let's make sure we label that. Gravity in what unit? Like I said, if we have meters, we would just change that number. How long does it take the ball to reach the fence? What's the first decision you have to make? X or Y. You have to choose that. So if it's going to reach the fence, is that horizontal or vertical? It's horizontal. So we're going to use x1. And what do we want x1 to equal? What's it going to equal? We want it to reach the fence. How far away is the fence? We're gonna, and when we see this, what are we solving for? Solve for t. If you take a couple seconds to make a plan, all of a sudden the math is easy, right? So we're gonna say 300 equals 103 t cosine 41. And what do we do to get t by itself? So y'all use your fraction button, right? So now this, this, and this are gone. And we have t equals, what do you get? See if you got what I got. It is possible that I hit the wrong key. I don't think I did. Now, is it reasonable? Is your answer reasonable? You've seen a baseball game. Parametric equations assume that you as a person living on Earth know some of these things, like you know what a baseball is. You've seen a golf ball hit. So if you came out with an answer like 23 seconds, should your brain tell you that that's not right? You've been to a baseball game. Does the ball ever take 23 seconds to land? No, right? So 3 seconds, does that sound okay? Did y'all get what I got? Okay. Now what about second one? How high is the ball at this time? Which equation are we using for height? What does that beginning tell you? Tells us we need to use y, correct? So what are we going to plug into y? How high is the ball at this time? So we're going to say, I'm going to plug it in just so you see it. Write down what you did in your notes. Now you're going to go straight into a calculator when you work on problems, but you may want this in your notes so that you're like, how did I do that? All right, what do you get for y1? I got 22.498. Type it in, see if you get that. Did you get that? Yes, I did. Okay, so does it clear the fence? How high is the fence? Yes. The fence is 10 feet tall. So, yes, he got a home run. Woo! Suppose there is a wind blowing at 22 feet per second in the direction opposite to the horizontal path of the ball. Find the new parametric equations, including the wind. Does the ball clear the fence now? I got a big question for you guys, a physics question. The wind is blowing opposite to the horizontal. Does the wind affect the y value? No, it only affects the x, right? So what is our new equation going to look like? Well, we've got the original. We're going to read this, though, opposite to the horizontal path. It's pushing against it. Oh. Now, if it's going opposite, are we going to add the wind or subtract the wind? It's going opposite, right? Let's look at why we do that, right? We're going to add the wind always. Why are we going to add the wind? If the wind is going opposite, that means it's going this direction. And what is cosine over here? What's the value of cosine over there? -1, right? Cosine is negative. So when we say cosine of 180, what are we going to get? -1. So is it going to subtract itself? Is it? It's going to naturally subtract itself, isn't it? Because cosine is negative over there. So that's one of the beautiful things about sine and cosine. You don't have to figure out whether to add or subtract, because depending on which direction it's going, it will be positive or negative, and it kind of naturally does that. Does that make sense? Okay. Find the new parametric, including the wind. Okay. What is y1? Did y1 change? Let's look at y, because I want you to believe me. Right? I still have gravity. Now, could I do this? I could. What is sine of 180, y'all? What's sine of 180? 0. So what's 22 times time times 0? 0. So this is going to just become 0. So you don't necessarily need it. Now this is because our wind is blowing opposite. So it's blowing at 180. If we start putting wind at different angles, things can change up, right? Okay, did that make sense? Not bad? Okay. Does the ball clear the fence now? What am I going to do? I'm going to repeat what we did here to see how far the ball went. So I'm going to pause this for a second and give you time to try that problem, and then we're going to talk about it. Oops. Okay, so what we did, because we want to know if it clears the fence, we're going to take 300 and set it equal to our new x, which includes the wind, right? This is wind. We notice that both of these have a t, so we can factor the t out and then divide, and we get 5.383 seconds. So what do we need to do with that 5.383 now to know if it clears the fence? We have to plug it into which equation? Where do we plug it in? To y, and it has to be how big at least when we plug it into y? Yes. So now plug into y1. If greater than 10, it clears. If less than 10, does not clear the fence, right? So you have to plug into y at that time and see how high it is. So when you take this number, 5.383, and you plug it in, what do you get? I got a negative number, but I didn't write it down, so I can't remember what it was. What'd y'all get? I'm giving y'all a minute to plug that in. Tell me what you got. First person done wins. Okay. Huh? I think so. What'd you get? That could be right. Okay. What does this mean to you? Well, can the ball be negative 99? No. So what does that mean? Ball hit ground before. That means if it could have traveled for 5 seconds, it hit the ground before that time was up, right? So your equation's telling you that it would have taken 5.383 seconds to reach the wall, but what does your height tell you? We hit the ground before that ever happened, didn't we? So what does this tell us? Did we reach the wall and go over it? No. We hit the ground long before we got to that wall. So we did not clear the fence. You know in your brain what's the smallest number we can get for y1? Negative 0, right? Since we got a negative number, that just means we hit the ground before then. This math will go on forever. I could plug 100 in for t if I wanted to, and it'll give me a crazy answer, right? Okay. The ball is not actually hit off the ground. That's called golf, right? And even that's not quite on the ground, right? You get a t. How would you adjust the equations to show the ball is hit when it's 3 feet off the ground? Is that going to affect x or y? Yes. x1 equals the same. What's the y1? Well, is this all going to be the same? 103t sine 41 minus 16t squared. How do you think I'm going to account for the 3 feet off the ground? Plus 3. All right? So this is gravity. This is starting height. Okay. Does that make sense?